Let's continue the discussion regarding the hydrogen bonding, and let's first talk about the origin of the hydrogen bond. The origin of the hydrogen bond, as we discussed in the previous Waals, we have this dipole-dipole interaction, and we have this instantaneous, sometimes referred to as transient dipole interaction. It's kind of temporary, very temporary. So the hydrogen bond is essentially a special kind dipole-dipole interaction. Okay, it's a very special kind. As we can see, if the hydrogen is connected with an element X, if this X has a very high electronegativity, if it has very high electronegativity with the elements like nitrogen, oxygen, and fluorine, so this resulting covalent bond between the hydrogen and the X will be highly polar. So they will be highly polar. Okay, so in a case like this, it will be the pair of electrons. It's almost going to be on the X, and very little is going to be on the H. So now you have the nucleus, a proton. It's almost a plus. However, there's still a covalent bond because of the pair of electrons. Even though this is very, very positive, this is still very, very negative. So this is a very, very strong dipole moment. So this, let's change the color. This hydrogen atom is essentially like a naked thumb with very positive charge, partial charge sticking out. So with any of those electron rich, generally the X groups, so this will bond to the other ones, this will bond this X, the resulting of that will be very, very negative. So you're going to have very strong interactions between this. That's the wrong color to choose. You have a very strong interaction between this. So this interaction is the hydrogen bond, and hydrogen bond only forms between hydrogen and nitrogen, oxygen, fluorine. When they are attached, it is stronger than normal polar interactions. If you have a normal polar molecules interact, it's weaker compared to the hydrogen bond. So this one is stronger. So polar interaction means this dipole-dipole interaction. You have a permanent dipole. And that's the reason why, even though hydrogen bond is sort of at its core, it's no different from a dipole-dipole interaction, because it's is actually fairly strong bond, a fairly strong interaction. So that's why it's being pulled aside to get its own category, So to actually summarize a little bit regarding intermolecular forces, okay, so now in terms of ranking of strengths, we first the strongest, we have the hydrogen bonds. Remember, hydrogen bonds can only happen between hydrogen, nitrogen, oxygen, and fluorine. And then we have the van der Waals. All the ones is called van der Waals. And we have the dipole-dipole. And this is the polar molecule. And then we have London dispersion. And those are for nonpolar molecules. Okay, so those are for the nonpolar molecules. Remember, this two is called the van der Waals forces. Okay, so just remember the hydrogen bonds, hydrogen bonding kind of special. And this is in terms of ranking: strongest, second strongest, third strongest. Let's have a quick example. Take a look at the following compounds and or the elements, and tell which are capable of forming the hydrogen bond. The first one, fluorine gas, F2, and methane gas, CH4, and water, H2O, and CH3Cl. The E, the last one, will be NH3. Okay, so those are the example. As we talked about the hydrogen bonding, we know it. Fluorine can't, because it doesn't have hydrogen. It does have hydrogen, but it doesn't have the other element. It can't. It has hydrogen bonded with oxygen, yes. It has hydrogen. It has hydrogen. It doesn't have the other one necessary, but this one it does. So the ammonia, it can form the hydrogen bond. And let's take a look at what actually the water forms the hydrogen bond. Water molecule is like this, and another water molecule will be like that. Because of this is highly polar, and this gives you the ability to form the hydrogen bond. And you can see, you can draw it. So this is a very strong interaction. Later on we can notice what will be the ramification for that. Same thing with the ammonia. Ammonia will have the shape like this. This is highly negative, but then you can have a hydrogen. Like that. But this can form hydrogen bonding. This is the hydrogen bonding. So this particular one is the H bond. Okay? And propagates, it actually forms a network. It actually forms a network. So then this plot shows very well the effect of hydrogen bonding. As we can say before, as we said it before, all the molecules will have London dispersion forces. So the London dispersion forces kind of goes up as the mass goes up. So that explains with the boiling point, H2TE is higher than H2SE, is higher than H2S. If you notice the S, SE, and the T and O, they are group 16 elements. So it's nicely joined about there, but suddenly you actually have this kind of abnormality, because if you extrapolate that, the water is probably should be right around, say, like -50, but however it's 100. Same trend is here for group 15. For group 15, you can see it's nicely trending down with the reduced mass, and suddenly it went up significantly. Okay, same thing with the HI, HBr, HCl, and suddenly HF went up this much. So those are normally caused by the hydrogen bond. Because only those compounds within those families are capable of forming that. This H2S can't, HCl can't, pH3 can't. And in this series, now it's following it nicely. So this is group 14 elements forming with the compound with 4 hydrogen. So it goes from the methane to silicon tetrahydride, germanium tetrahydride, tin tetrahydride. So the boiling point moves up. So this is actually the London dispersion forces at work. The other one is kind of a practical aspect of why hydrogen bonding is so important. Shown here, DNA double helixes. How those base pairs can recognize each other. This is the fundamental step in controlling life. So all this, the base pair recognize each other, T with A, C with G. How is that happening? It's by those hydrogen bonding. T and A got two hydrogen bonds by recognizable, and C and G, now you have 3 pairs, 3 hydrogen bonding. So T cannot bond with C, A cannot bond with C, vice versa. C cannot bond with A, or G cannot bond with T, and G cannot bond with A. So that is achieving that critically important, the base pair recognition. It happens over and over in the biological system. So the hydrogen bonding is a crucial one. That is a crucial interaction. It's vital for living organisms. So to actually wrap up this particular section regarding how we're going to see these physical properties. Let's erase this to like the color. Erase that. Oops, that's the wrong way. Give me the right color. So to see those physical properties, so far we're focusing on the melting point and the boiling point, but there are others. Actually, the principle are the same. You will have surface tension, and you have viscosity. Okay, later on miscibility. All is related to the interactions between the entities. So the physical property, let's focusing on the melting point, boiling point. Those are one interactions, right? So the particular flow chart for if we want to resolve those issues, we look at melting point, boiling point, and we go through like this flow chart. If you're looking at the pure substance, Is it a metal or ionic compound? If yes, strong interactions, high melting point, boiling point. If no, so then we're dealing with covalent / molecular compound. Alright. Hydrogen bond. If it's a yes, fairly high. Melting point, boiling point, but much lower than the ionic or metallic one. But if no, it's the molecule polar. If yes, then you have dipole. This is slightly higher. But still much lower than that. If the answer for that is no, now is nonpolar molecules. So the London dispersion forces. And it scales with mass. So this one will have the lowers. Okay, so then this is essentially the flowchart of your handling when we do the physical property comparisons. And with that, and I'd like to wrap up this podcast and go and complete the worksheets to reinforce what you have learned. Thank you very much for your attention.